Okay, so let us get it going. Good evening, everyone, and welcome back to today's set colloquium, which is titled as Hydrogen Bonding that turns the DNA and folds the protein as spectroscopist's delight. It's interesting to note that an undergraduate student is attributed for its inception way back almost 100 years, more than 100 years ago. And it's also interesting to note that there are many interesting facets of this bond that not only connects two other atoms at the same time, but also actually this connects physics or chemistry or biology, whatever way you talk about the science in general. And what we are going to hear today from Himansu is that while a lot of things obviously is understood, but there are also a lot of advancements and in the experimental techniques and also the methods which are now used to understand the hydrogen bonds. And he's also going to take us through some difficulties and challenges that are faced in carrying out the spectroscopy of hydrogen bonded molecular clusters. Just to say a couple of words about today's speaker, Himansu Biswal is an associate professor of chemistry at the School of Chemical Sciences, NISER, Bhubaneswar. And he received his MSc from Department of Chemistry from Utkal University way back almost 20 years ago, and his PhD from TIFR under Professor Sanjay Vatagankar, who is also there on the call. Welcome, Sanjay. That was in 2009, and then he moved to, okay, I'll not try to kind of pronounce this, but I think it is something of Atomic Energy Commission of France, which is CAA, for the first postdoc research with CNRS postdoctoral fellowship, and also a second postdoc at the University of Michigan, Ann Arbor in USA. And he joined the School of Chemical Sciences at NISER in 2012. That is about 10 years ago. And he involves deeply in building scientific instruments. That is, in fact, the flavor in which this particular colloquium, asset colloquium, is actually scheduled. His current research interests include salvation and isomerization of peptides, conformational landscape of flexible biomolecules in jet-cooled condition, and sulfur, selenium, carbon center, hydrogen bonds, and their role in the structure and function of biomolecules. So we can definitely look forward to very interesting experimentalist view of the whole field. And so I now, without further delay, invite Himansu to start his colloquium.
Okay. Thank you, Dr. Satyanarayan, for inviting me to give this colloquium lecture. I'm really thankful. I have never thought of I'll give a colloquium lecture in TIFR, and I'm really thankful for that. So in next 30-40 minutes, what I'll do, I'll talk about a little bit history of hydrogen bonding, and when a spectroscopy become very happy when he or she sees the spectra. So this one, the hydrogen bonding is really very old, and I'll say something about hydrogen bonding. So this one, not my statement. It was by somebody, which the statement was given in 53 years ago. So this is what he said. It is my prejudiced belief that except for electron pair bonding between atoms and Coulombic attractions and repulsions between ions, the most important structural principle in chemistry and biology is that of hydrogen bonding. So hydrogen bonding is also of great importance in physics, not only in chemistry and biology. It is in physics, crystallography, mineralogy, geology, meteorology, and various logologies. So I therefore take the pride in the fact that I was the first to introduce the hydrogen bond concept, the idea that a hydrogen atom can be bonded at the same time to two other atoms, and that was 50 years ago. So he introduced the speaker in this lecture actually, which was given in 1969. he's the same speaker also. He introduced something called non-bonded electron, and he introduced the coined the word lone pair of electron. Okay, he said that lone pair of electron can participate in hydrogen bonding. It attracts a positively charged proton. So who is that speaker? So he is none other than an undergraduate. So and his name is Maurice Huggins, and he discovered hydrogen bonding about 103 years ago, and it was in May 1999. And he was doing, at the time he was doing his undergraduate at the University of California, Berkeley with Professor Williams Bray, and he was about to write a term paper that Professor Bray asked for, and he was not he was not finishing in writing the term paper. And when Bray asked actually to submit that one, in a hurry, he said he showed the notes he had made, and the notes are from the lectures Bray had taught in the classes. So those notes contains unsolved problems in chemistry, and Bray went through the notes, and he said there are several interesting ideas in this paper, but there is one you will never get chemists to believe, that the idea that a hydrogen atom can be bonded to two other atoms at the same time. So this is the drawing actually. This is the drawing of a hydrogen bonded dimer, and that is the hydrogen fluoride dimer. And this is what he proposed, Huggins proposed, how the hydrogen bonded dimer of HF2 can look like. Okay, this is the handwritten drawing, and it is taken from this notes. So Maurice Huggins, he was not only famous for hydrogen bonding. He was a brilliant student, and later he became a very notable scientist. So he is famous also for the Fleury-Huggins theory. That is one of the theory used in polymer chemistry or polymer science. And he also produced the first model of alpha helix in 1943, way before than Linus Pauling, Robert Corey, and Branson. So he is the Maurice Huggins is the first one, and it is again an undergraduate student who proposed the word hydrogen bond. So when he proposed, actually he got many acceptance. Many people started believing the hydrogen can bond two atoms at the same time. It was actually in 1920 in a paper in JAX, here in this paper. So Maurice Huggins, the Latimer and Rodebus published the paper about the hydrogen bonding, and there in that bonding, in this paper, they cited in the footnote, they cited Maurice Huggins' work, and Maurice Huggins said that the term paper was never published. That's why people thought of thinking Latimer and Rodebus was the first one to give the concept of hydrogen bonding. It's not, it is the Maurice Huggins who gave the concept. Later on, it was again proved experimentally by Langmuir, and then there were criticisms also. Many didn't like, and one of them was Professor Henry Armstrong, and he said the hydrogen cannot be bonded to two atoms at the same time, and he ridiculed the idea and saying the statement the hydrogen could act as a biochemist. It's not possible. So then again, this Latimer Rodebus was largely dismissed or ignored for at least 8 to 10 years. And then it is the Linus Pauling paper in 1925 paper, where he explained the structure of HF2 minus, and the structure could be explained by the hydrogen bonding. And the famous book, The Nature of Chemical Bond, actually cemented the concept of hydrogen bond. So it's because of Louis, it's because of Linus Pauling, people started believing on hydrogen bonding, and they and did the research further. So this is the 1920, the famous paper on hydrogen bonding, the most probably the first one. And they were looking at the associated liquids, mostly trying to explain the liquefaction of substances. And this is again the water dimer or water structure was really puzzling that time, and still it is also puzzling. So in that paper, they stated actually both of them, Latimer and Rodopus. So water is a little different than HCl, hydrogen chloride and ammonia. Water occupies an intermediate position, and it has tendency to give up hydrogen as well as to add the hydrogen, okay, with a balanced manner. So such an explanation they gave this one. This hydrogen could be here, could be held between two oxygen with a weak bond. They call it weak bond, and that bond leads to later on as hydrogen bond. Again, this water molecule, it was again in 1931. It's by Linus Pauling, who tried to explain not only the dimer of water, tried to explain the multimers of water through hydrogen bonding. And he told in that paper, he told the hydrogen bonding is completely electrostatic in nature, and those atoms who has high electron affinity, they can form only hydrogen bonds. So most probably this is the famous book on the nature of chemical bond, in chapter 12 and page 449. He actually mentioned the concept of hydrogen bonding here. And again, this is supposed to be one of the finest definition on hydrogen bonding. So for the XHY, here the X, if I take oxygen here, oxygen is X, and the hydrogen is hydrogen, and the Y is another oxygen. For the XHY hydrogen bond, both X and Y should be electronegative. Okay, so oxygen here, both X and Y are oxygen, and they are electronegative, and the XY distance should be shorter than the corresponding sum of van der Waals radii. So van der Waals radii of X and Y. Okay, and this interaction is mostly electrostatic in nature. So here comes again on this paper actually. So not only the paper, actually they wrote the book the hydrogen bond. This is most probably the first book on hydrogen bonding in 1960, and that book there was a review by Maurice Hawkins on the book written by Pimentel and McLean, and he said hydrogen bonds are strong enough to be a great importance. At the same time, it is also weak enough to participate in chemical reactions, and it brings out many physical changes. So then in this book, actually this is 1960 book on hydrogen bonding, they defined give another definition of hydrogen bond. So here they are not limited to the atoms. A hydrogen bond is said to exist, the definition says, a hydrogen bond is said to exist between a functional group AH and an atom or a group of atoms B in the same or a different molecule when there is evidence of bond formation, association or scintillation. There is evidence that the new bond linking AH and B specifically involves the hydrogen atom already bonded to A. Okay, so this one again they also said in this book, this concept will have a bright future, and they said this possibility of such fundamental gain, again actually this is a hydrogen bonding, to the appeal of an area which remains one of the most interesting interaction of chemistry and the study of hydrogen bond. So 1960 also they realized the hydrogen bond actually will change many concepts in chemistry, and it's true also. Again, so after 50 years of discovery, this paper was published. Again, it was published. This review article was published by Maurice Hawkins, the discoverer of hydrogen bond. So I'll read the last paragraph of that paper, which is exciting. So in concentrating in this article on the aspects of subjects in which I have myself been most interested, I have not intended to belittle the great contribution to the development and applications of hydrogen bond, a theory made by thousands of others. Much fine work has been done, okay, yet much more obviously remains to be done. So this was recorded in 50 after 50 years of hydrogen bond discovery, and the last sentence says, after 5 years also there are a lot of fine works have been done, and that time he predicted there will be many more unsolved problems are there. So in next 10-20 minutes we see how many problems we have solved and how many are there to be solved. Okay, so then many stuff, hydrogen bonding is not new, it's obvious, many researchers have been done. We start our day also with hydrogen bonding. To wake up from the bed and go to the tap, go to the washing basin, open the tap. So you'll have water droplets, and water droplets contains many hydrogen bonded clusters of water. So now the new year is coming, so we'll have a lot of celebrations. And the celebration in the glass you have alcohol, and that alcohol, if I zoom it up, look at the molecular level, so it is not only the ethanol, it is hydrogen bonded clusters of ethanol water, and many more. So when you have fever, I have taken some example, it's there everywhere from our day-to-day life. So if you take paracetamol, for example, if you look at the crystal structure of paracetamol, so it's a hydrogen bonded crystal. If you look at proteins, so there are a lot of amino acids which are bonded to hydrogen bonds. In sugars also there are a lot of hydrogen bond. It is not only in the materials, it is there in our genes, in our cell, in our DNA. So if you zoom up the DNA, you will have a base pair, and this base pairs actual pair they paired up to hydrogen bonds, double or triple hydrogen bonds. Okay, so it's not only in our day-to-day life, it is there. So the concept is so established, it's there in our textbook, or it is there in the high school textbook. I have taken the example, this is the NCERT 11th standard book, and it is in the unit 4. If you look at, they have given the definition, okay? So they have also followed the definition of Pauling, most probably. So this definition says hydrogen bond is formed when a hydrogen atom finds itself between two highly electronegative atoms, such as chlorine, oxygen, and nitrogen. So they are limited to fluorine, oxygen, and nitrogen. It may be intermolecular or intramolecular. And the hydrogen bonds have powerful effect on the structure and properties of many compounds. So this is very preliminary in the textbook, in our high school textbook. This is how they define. So if I have a hydrogen bond system, if I represent like X, Y, so the X will be electronegative, Y will be electronegative, and the X could be fluorine, oxygen, and nitrogen, and Y could be also fluorine, oxygen, and nitrogen. That's what our textbook, the Pauling definition, the Pimentel also says till now. So these are the typical questions they ask in the 11th or 12th standard exams. So why hydrogen fluoride is liquid? Hydrogen fluoride has high boiling point than the HCl other stuff. Why H2O is liquid? Ammonia has a higher boiling point where pH 3 is not, and some book they mention pH 3 cannot form hydrogen bond, though it's not true. Ethanol has a higher boiling point than diethyl ether, because ethanol forms hydrogen bonding. Again, it is also applied in solubility. Alcohol dissolves in water because of hydrogen bonding. The example I gave, the wine glass. The viscosity and surface tension are also related to hydrogen bonding. So if you have a stronger hydrogen bond, you have a bigger complex, and it moves slowly. You will have a viscous solution or viscous liquid. You have a cage-like structure like our proteins or DNA or molecular cages. So you have those cage formation can be possible through hydrogen bonding. These are the simple questions asked in our textbooks based on hydrogen bonding. So after that, the progress was huge. People have started and writing books. There will be 100 books on hydrogen bonding, even if the titles are hydrogen bonding. So the left side, the left one is the 1960 book, and that was by the Pimentel. And till the 2022, this one again, the newer version of the payment book, actually, the Kindle version. So there are plenty of books. I have picked a few of them. There are plenty of books. That means the progress on hydrogen bonding is huge. Okay. So hundreds of books are there, but not only hundreds of books, there are hundreds of thousands of articles are there. Research articles are there. So then what is left to understand? This is because of the enormous research on hydrogen bonding that led to IPAC to think about to redefine the hydrogen bonding. Again, the task force was made in 2011, and that's the definition was given in 2011. And this task force was led by one of our Indian scientists, Professor Arunan from IIC, and they redefined the hydrogen bonding. And the definition says the hydrogen is almost like a combination of Pimentel and Pauling's definition. The hydrogen bond is an attractive interaction between a hydrogen atom from a molecule or a molecular fragment XH, in which X is more electronegative. Always I am highlighting the electronegative part because the latter of my talk will deal with the electronegativity. So the XH in which X is more electronegative than hydrogen, an atom or a group of atoms in the same or a different molecule in which there is evidence of bond formation. So there are a lot of criteria whether there is evidence of bond formation or not. So they have used the geometrical criteria also. The distance will be less than the sum of the Vander's radii. So this why I have taken the chalcogen group. So that's why there are two lone pairs. So for oxygen, for nitrogen, there will be only one lone pair. So this figure is for the chalcogen groups. So they also, this is the IPAC notations. They depicted the hydrogen bond with the 3 dots in between hydrogen and Y. The XH represents the hydrogen. This XH, this is the hydrogen bond donor. So the acceptor can be atom, can be a molecular fragment, and they also mention if the Y should be electron rich. Okay, it will not be limited to a lone pair or pi bonded pair. It can be anything, but it should be electronegative. Okay, so why we were interested to look at less hydrogen bonds with the less electronegative atom, we came across this paper here. So this is again the review article. It comprises many hydrogen bonding clusters. This one, if you look at this figure, you will have the hydrogen bondings with the sulfur, which fall in the region of weak hydrogen bonding. Okay, so that we thought actually we will look at this one. That time the hydrogen bond sulfur was not studied in detail. We thought of looking at this interaction in detail through doing a lot of spectroscopy and computational studies. So if you look at why I said the sulfur forms weak hydrogen bond, this was well accepted. So if you go by the electronegativity, this is the table which represents the electronegativity and polarizability. Going from left to right, the electronegativity increases, and going from top to bottom, the polarizability increases. If you go down, oxygen, sulfur, selenium, tellurium, and polonium. So hydrogen has electronegativity of 2.2, while the polonium has electronegativity of 2, which is less electronegative or electropositive in comparison to hydrogen. Sulfur, going from oxygen and to sulfur, that is about 30% of reduction of electronegativity. Okay, so that could be one of the reasons why people were thinking sulfur will form weak hydrogen bond. So how to establish whether there is hydrogen bond formation or whether the hydrogen bond is weaker or stronger? These are the few stuff we look at. One is called the binding energy. You take a monomer, you take a dimer, and you subtract the dimer energy. You subtract the monomer energies from the dimer energy. So that's called the binding energy, and that binding energy, if it has a quantity binding energy, then it is double. So that should be, so mostly we do rely on the quantum mechanical calculation. If you are solution phase experiments, you can do the ITC. There are some other gas phase experiments also to find it out the binding. Then there should be electron density between the interacting atoms like H and Y. There should be development of some electron density which we can verify doing the quantum mechanical calculations and XRD also. There should be donor acceptor overlap, which we can verify with the IR spectroscopy. There should be the donor acceptor means the lone pair will be the donor and some empty orbital like the antibonding orbitals will be the acceptor. So that should be change in the chemical shape. So if it is hydrogen bonding, the proton, there should be change in the chemical shape of the proton. It could be most of the time it is downfield shifted, and there could be change in the stretching frequency. If it is XH, the XH will be observed for the complexes. It will be observed in the lower frequency region. We call it is redshift with respect to the monomer XH stretching. And that one we use the IR spectroscopy to find it out whether it is redshifted or not. And the problem is actually, so to study the dimers, so you have to stabilize and detect the dimers. And the conventional spectroscopy, I'll talk about those, is not sufficient enough actually to study those dimers in detail. Okay. We rely on some other spectroscopy that is called supersonic jet spectroscopy, which should have a lot of instrumentations. Okay, so this is what the experimental strategy. I will go quickly. So this is the this one shows the energy, potential energy called for the dimer in the ground state and excited state. So what do? We excite the monomer and record the excitation spectrum. We excite the dimer and record the excitation spectrum. So the lowest energy transition in the excitation spectrum is called the band origin, which is written as BO. So from the band origin, we'll have the band origin for the monomer, we'll have the band origin for the complex. So from that we can have idea whether the complex is formed, if it is formed, whether it is stabilized in the ground state or excited state. That information we can find it out. From the excitation spectrum also, we can find it out the intermolecular stretching, which is denoted as sigma, and this intermolecular stretching is here. This is the vibration between this monomer unity and the other monomer. Okay, so we can have this intermolecular vibration information from the excitation spectrum. We can have, if we excite, we'll use the IR sources. We can measure the IR frequencies. Mostly, this is the XH. Here is the OH. So OH stretching frequencies can be measured by doing the IR spectroscopy. So this spectrum represents the excitation spectrum. This molecule is called paracrystal, or the monomer. This one is the excitation spectrum of paracrystal inside hexane, and you can see this is a very broad spectrum with full width half maximum is 1600 wave number. We have recorded the paracrystal, the IR spectrum of paracrystal, and the OH stretching frequency, OH stretching is a very broad, and the full width half maximum is 300 wave number. If you look at carefully, the shift in the band origin going from the monomer to the hydrogen bonded dimer, it happens within 100 to 1000 wave number. Okay, typically. So if your spectrum is 1600 wave number, both your monomer and complexes, this intermolecular stretching, everything will be buried in this wider spectrum. So this one, the XH stretching frequency is going from monomer to monomer. It is a 20 to 30 wave number redshifted most of the cases. And if you have a very broad spectrum for the monomer itself, you can never observe the dimer. Okay, because you have it will be buried in this spectrum here. So similarly, the intermolecular vibrations about 30 to 150 wave number. And you can never have from the excitation spectrum in the solution phase excitation spectrum, you can never extract the information about the intermolecular stretching. What we need, to achieve this, to have actually the molecular view of these hydrogen bonded clusters, we should have a high resolution spectra with smaller probability of maximum. We should have very, very low thermal energy so that the complexes will not be dissociated. There should not be solvent effect. and we should have mass selectivity. So here I don't know, it is coming from the monomer, it is coming from the dimer or the complex. So we should have the mass selectivity. So all these criteria we should have to study the hydrogen bond complexes in detail. So it is not that easy the way we think of. So to do the experiment, it takes a lot of time, it takes a lot of energy. This is what. Here comes to get rid of the bonding, all the stuff. So we use gas-phase laser spectroscopy. It is also called as supersonic jet spectroscopy. This is a molecular beam experiment. So we first vaporize the molecule through desorption or the thermal heating. Then it is backed by a vapor gas, either helium or argon. Then it is expanded through a orifice, and the orifice, very small orifice, from a high pressure to low pressure through a smaller orifice, it forms a molecular jet. And doing so, actually, we cool the internal degrees of freedom, mostly the molecular rotation and vibration, and the rotational and rotational temperature we can go to 10 to 15 Kelvin. Okay, with this expansion. Since the concentration of the molecule are very, very small, so there will be not, we can detect the single molecules through this spectroscopy. Here in this one, we can do the fluorescence spectroscopy, and the other part of the chamber here, we can do the mass spectroscopy. So when we have the UV sources, when we use the UV sources, we record the excitation spectrum or the mass selected excitation spectrum that we call the REMP. There you will have the information about the band origin and the intermolecular stress. Then we use the IR source or IR laser to do the IR spectroscopy using the IR UV double resonance spectroscopy or IR UV whole body. So this is most more clear picture. This is our sample holder here. This is the picture from NISER what we built here. So this is our sample holder. Here we expand. We have a skimmer here, and then the high voltage grids for the time of flight mass spectrometry. So I don't have time actually. It's in technical details of this spectroscopy. So in brief, what we can achieve with this one, we can cool down the molecule to 10 to 15 Kelvin. We can reduce the spectral bottling and the congestion. We can get a very high resolution spectra, and the typical fluid top maximum is 5 to 10 wave number, which is at least 1000 or 100 times, you would say, 100 times smaller than that of the spectrum obtained in the solution phase. We can study the weak, since the temperature is very small. We can study the weaker molecular complexes which are not stable at room temperature. We can record the main advantage is we can record. This is one of most probably one of the spectroscopy where you have the mass selectivity for IR and UV spectroscopy. So this one I again compare. Okay, so these are the three molecules I compare. One is the monomer paracrystal. This is the hydrogen bonded paracrystal and water cluster. This is the paracrystal and methanol. So the black trace represents the paracrystal in hexane, the excitation spectrum. When we use the supersonic jet spectroscopy, you can see how narrow it is in comparison to the solution phase spectra. Now, this is again, as I said, it's mass selective. We can get at the paracrystal water channel and record the spectrum. This is narrow. Paracrystal methanol also is too narrow. Then
Himansu?
there is this laptop hanged, so.
Oh, okay.
Just a minute, it's coming up. Okay. that. Okay, so this is the air spectra. I'm sorry for the interruption. So this is the air spectra we recorded. So the broad one, the black trace again in solution, and this is the narrow peaks are in gas stage in with a supersonic jet condition. Okay, with a jet pool spectrum, you can see how narrow it is. So if I combine all of them, all of them will be there in this the condensed spectral envelope. Okay. So this is what we can achieve using the supersonic jet spectroscopy. Sorry, this laptop has.
Does it take a lot of time to pull the images? Is that the problem?
No, there is not a bigger size images.
That's
Might be the virus or scanning is going on, looks like it.
Can't you halt it for a while? The scans.
Okay. It's clicking, it's a. Should I restart this one?
Himansu, you can go Control Alt Delete and Task Manager and kill this virus scan.
Someone is coming in.
This one.
You can close
So we have to close and join it again.
yeah, no, you can close this Microsoft PowerPoint, which is not responding.
Okay.
No, it's yes.
Now start.
So here you just see like what Sanjay said, you just see what are the processes that are running and you can kill them in case, like if you go to task manager. By right clicking on the toolbar and then see the task manager and switch off.
Okay. Is it visible now?
Yes. Now back to normal. Yeah.
Okay.
Perfect.
Okay, sir. Again. So I took the help of library. I would have done in my desktop anyway. Okay, so this one, if I compare the characteristic in hexene, the medium is hexene, and the gas phase. GP stands for the gas phase, the supersonic jet condition. So the full width half maximum is about 1500 to 1600 wave number. For the excitation, mostly the fluorescent spectrum. For our case, it's about 4 to 7 wave number. So for IR, it is 300 to 350 wave number, and we get 5 to 10 wave number. So now we can imagine what is the resolution we can get from the supersonic jet spectroscopy. So hydrogen bonding, this with sulfur, we started a long back. When I joined in PIPAD, I'm really thankful to my PhD guide, Professor Vategankar is here today. So we started with a very small complex, then we moved to bigger complexes, then we moved to in solution. And in next few slides, I'll show what we did. And again, I want to show this slide. This is again 2 years back, IIC Bangalore, they celebrated the 100 years of the Latimer and Rodebush paper on hydrogen bonding. And this is the cover page of the Journal of Indian Institute of Chemical Science. The hydrogen bonding sulfur is very interesting and elusive. If you look at it, the sulfur can be, this is the smallest dimer with sulfur and has huge binding energy. So if you remember while doing the introduction, I said people were thinking sulfur can form weak hydrogen bond, but it is not the case. Sulfur can form, this hydrogen bond with sulfur can be as big, they are in a big molecule as big as pyridoxine proteins, okay, pyridoxine or rubidoxine. So again, so here they mention in the IPAC definition, X and Y should be electronegative, and we will show you not only the X can be electropositive. Okay. So it's really very interesting, the hydrogen bonding. So we started with, as I said, we started with the small molecular complexes just to mimicking the interaction of the amino acid tyrosine, tryptophan, and methionine. So we have chosen these model complexes. Then we move further to have the peptides. Then we looked at those interactions are there in also in proteins in bigger molecules. Okay, so this one we started with a smaller alcohol and versus thiol. So this is our hydrogen bond donor characteristic. The waste is the donor. Here the water is the acceptor. Here H2S is the acceptor. What we looked at, this trace are the vibrational the air spectrum actually. It gives information. This is the monomer, and the left side represents whether the vibrational frequencies are red shifted or not. If you compare water to sulfur or H2S, in this case you have a OHS hydrogen bonding, the other case you have a OHO hydrogen bonding. What is happening?
It somehow looks like taking time to load the slides.
Sorry?
It looks like it is taking time to load the slide, I said. Unless, are these images a bit high resolution?
No, not at all. These are only
then there must be some processes going on at the back. Now it is fine.
Coming.
Are you still?
I'm really sorry.
No, it's fine, but I'm wondering whether some other process once again started catching up. You might want to, do that and continue sharing your screen. And then can you do the right click on the taskbar and get what the processor going on right now?
Yeah. No, nothing much actually. The processor.
You're saying there's no processor which is hogging a lot of CPU bandwidth?
No. Nothing is there. Somehow this Microsoft is stopping.
I see.
It's not.
Then it should not have any problem. Do you want to quickly, you could run a PDF if you like, but then you may not have the flexibility to run for animations or, slide by slide.
Yeah. This is my mistake only. I thought this library, they have set up the new stuff. So I thought I'll come, it will be better. I would have given in my desktop only.
Yeah, it's okay. Sometimes technical things do happen. So if you, one possibility is you try PDF if you want to build a PDF and run. Or if the file is not big, you can also share the file with me. If you want me to, I can do it from here.
That we could have done actually. Is it visible now?
Yes, visible.
Okay.
Your what I told you, the other screen is also visible now, but if you think this is better way, you can go ahead.
Oh, it's fine, not a problem.
All right. Okay.
Else we can do. Yeah.
Himansu, how big is the file? PDF, sorry, PPT.
Okay, so let's do in this mode. Is it fine? Let's share. Okay. Okay. Is it fine, this one?
Yes, it's in the regular mode, right? It's okay. So if you're one of your students or somebody has a PPT, they can send me by email quickly. I can share the slides for you.
Oh, this one is coming.
This is fine. We move slides a bit back and forth.
Let's find this one.
Yes, it's going
The
on.
right hand side is coming.
Yes. Slide number 29. Yeah, it all looks okay. So far, so good.
Okay. Okay.
Yeah, but parallelly, if possible, ask one of your colleagues or students.
It's sending.
Possible.
Okay, so let me continue.
Oh, yeah, sure.
So then we changed from alcohol to, this was the alcohol, and to thiol. The alcohol are oxygen acceptors. The thiols are the sulfur acceptors. So we found actually the OH-O hydrogen bonding in these cases are little stronger than the OHS, but nevertheless, the way we are thinking like H2S dimer, the hydrogen bonding with sulfur will be weaker, and it didn't happen so. Then we switch to from alcohols to ether, and if you look at, this is water, and we symmetrically substituted hydrogen with the methyl, ethyl, all the stuff. If you compare water with H2S, water forms stronger hydrogen bond. If you compare dimethyl ether and dimethyl sulfide forms stronger hydrogen bond than the dimethyl ether. Similar for the diethyl ether and the tetrahydrofuran and tetrahydrothiophils, they form very similar hydrogen bonding. So it said it's not the oxygen will form stronger hydrogen bonds. The sulfur also can form stronger hydrogen bonds. Then we came across this paper actually. It says again, this is about the proteins, and they say the methionine sulfur is a poor hydrogen bond acceptor. And this is obvious. Going by the electronegativity, as I was telling, it is obvious. Then we checked actually, we constructed a peptide which contains a methionine residue. This methionine sulfur can form hydrogen bond. At the same time, in this peptide, you can have the NH pi interaction, you can have NHO interaction, you can have NHS interaction. So this is one of the ideal system to probe whether the NHS interaction is stronger or weaker with similar conditions, same molecule. And what we observe, this is the free NH2 going from right to left. Actually, this is the vibrational frequencies become smaller, the bond strength become the NH bond strength become weaker, and the hydrogen bond strength becomes stronger and stronger. Okay, if you go by the IR spectroscopy. So what we observe, the red line corresponds to this frequency. These are the computed spectra, and the upper trace are the experimental one. And what we observe actually for almost all the cases, the NHS hydrogen bonding is strongest among all other hydrogen bonds present in that peptides. So this is what we observe in the peptides, and we went and look out to the proteins. What we found, this type of folded structures also we located in proteins. It is not in simple molecules or small molecules. We started with a simple dimer, we went to the peptides, then went to the proteins, and we observed in many places, in several cases, this NHS hydrogen bonding is equally strong as NHO hydrogen bonding. Again, then we move further down the group, and the selenium, we studied the selenium hydrogen bonding. If you look at, so this one compares the NH pi hydrogen bonding, NHO hydrogen bonding, NHS and NHS selenium hydrogen bonding. So here also we found the NHS selenium hydrogen bonding is a little weaker than the NHS hydrogen bonding, but it is not as weak as we were thinking before. Okay, it can form also stronger hydrogen bonds. Means the hydrogen bond strength is more than the water dimer. Okay. So this is one of the solution spectra, actually solution binding energy doing the NMR spectroscopy. We compared the NHO hydrogen bonding and NHS hydrogen bonding, and we found the NHS hydrogen bonding is 15 kilojoule per mole. The binding energy is comparable with about 16 to 17 kilojoule per mole for NHO hydrogen bonding. Okay, so then we move further again to tellurium and polonium. We are going down the group. If you look at here, the electronegativity decreases. Experimentally, we confirm the sulfur, dimethyl sulfide can form stronger hydrogen bond. The selenide also can form stronger hydrogen bond. What about the tellurium and polonium? So which has less electronegativity compared to the hydrogen? So this is again, we don't have any experimental data for that, but we looked at the crystal structures and we found many examples where you can have hydrogen bonds with the tellurium. Okay. So then we choose many hydrogen bond donors and hydrogen bond acceptors, and what we observe, both tellurium and polonium, these are the computational NMR and IR spectra. So if you look at, this is from the monomer frequency, all of them are redshifted. Okay. So the polonium is the last one, which is 150 wave number redshifted. If you compare with the oxygen counterpart, it is 170 wave number redshifted. Okay. Similarly, so it has all the characteristics of hydrogen bonding. So the wave stretching frequency is redshifted. The proton, the NMR chemical shift is a downfield shift. Okay. So this is tellurium and polonium, theoretically at least till now, it can form also hydrogen bonds. And this is bit weaker, but not the weakest hydrogen bond. So then let's come back to the IPAC definition. As I said, I will emphasize on whether the only electronegative atom can form hydrogen bonds. So if you look at the XH, X is more electronegative than hydrogen. This is the IPAC definition says. So then we thought of, we look at the metal hydrides, manganese, iron, and cobalt. So this X we can replace with manganese, iron, and cobalt. So the electronegativity of manganese is 1.5, iron is 1.83, cobalt is 1.80, which is far less than the electronegativity of hydrogen. So with respect to hydrogen, they can be called as electropositive elements. So is it possible to have this type of hydrogen bonding? We did so. We took these molecules, so just to polarize this hydrogen bond, and even if we did the calculation, doing a lot of different calculations, we also found this hydrogen always carries a negative charge, but it is possible, it forms the hydrogen bond with the oxygen, sulfur, and selenium. So oxygen is the weakest actually because of the electrostatic repulsion. And here there is a little bit of a dispersion component of sulfur and selenium, which stabilize this hydrogen bond, and we can have a hydrogen bond of MHYZ type. Okay, so this is again, I am showing this one, comparing with the different, with water, with H2S, with H2SE, dimethyl ether, dimethyl sulfide, and dimethyl selenide. You can see these hydrogen, these are redshifted in comparison to the monomer frequency, and we have many correlations the people use for the hydrogen bonding, and we observed all the typical characteristics of hydrogen bonding. So it's possible, at least theoretically till now, it's possible to form hydrogen bonds with metal hydrides. So then we came up another stuff. So whether without lone pair or pi electrons can we have hydrogen bonding? So we looked at this molecule actually, the crystal structure was reported. If you zoom it up, we'll find the crystal structure, there are no hydrogen bonds, there are no other interactions, no pi electrons. So they are very close. Two monomers, if you take, they're very close to each other and they are interacting to carbon and hydrogen. Anyway, this carbon is called inverted carbon. It is not the carbon actually like CH4 or ethane molecule. It's called the inverted carbon. We did further analysis. We found actually there is a substantial donor and acceptor overlap of this hydrogen and this sigma star orbital. So we took this model compound and did further calculations. So what we found, this sigma electron goes to, this sigma electron goes to the antibonding orbital of CH. At the time, this sigma electron goes to the antibonding orbital of CC. So this is a two-way process. Earlier, whatever hydrogen bonding I discussed, those hydrogen bonding is only one-way process. Either the pi electron will go to the sigma star or the lone pair of electrons go to the sigma star. Here, both sigma electrons are going to the both way. The process is both way. So you can have a CHS, C sigma. So the I stars for the inversion. You can have this one. So if you take this one and compare recently published or recently coined another non-covalent interaction called the carbon bonding, and this one is very similar to the carbon bonding, this part. If you compare the other part, it is very similar to the hydrogen bonding. So we coined this term, and we gave another name for this bond, and this is called the carbohydrogen bonding. Anyway, so we compared with other stuff, and we found it has a sufficient energy. It's not weak actually. Its energy, if you compare, it's 15 kilojoule per mole. It is very comparable to the water dimer energy. Okay, so this is a new type of interactions which is possible without lone pair or pi electrons. Okay, then we thought whether this type of interaction has already reported by doing the literature survey. We found this paper, and this paper was published in Science. It was written by one of the famous scientists, the Nobel laureate Francis Fernando. What they explained, actually, they were doing the enzymatic activity and doing different mutations. So when they mutate one of the valine with phenylalanine or tyrosine, they saw the turnover. Actually, the enzymatic activity increases from 1.5 to 2 times it increases. And they explained it's because of the intermediate stabilization because of the pi-pi stacking. So when they mutate the serine with the alanine, serine has a OH group like here. Alanine doesn't have a OH group. Okay. So when they mutate, they also found there is a turnover number, actually, the increase in the enzymatic activity, and it is 2.5 times. Okay. So what is happening? They didn't have any explanation. If you look at, I have highlighted in red, they don't have any explanation for this part, this mutation, and they left it as it is. Then I thought we'll do the calculation and see is there anything we can explain through our carbohydrogen bonding. We did the calculation, what it does actually. So this is the product, the inverted carbon product. Here, the serine has a OH group. It forms a carbohydrogen bond with this inverted carbon, and it stabilizes the product actually. It doesn't allow the product to move out of the enzymatic core, and that when they substituted with alanine, this bond breaks and the product comes out and the turnover number increases. So this carbohydrogen bonding concept could explain this one. After that also, we did other calculations to verify, and we found this energy could be around 20 kilojoule per mole. Then I communicated to them, this is what we are trying to explain. I am really thankful to them, they replied. So this is the reply we got. I'm not claiming this carbohydrogen bond to explain, that could be anything, because this is a very enzymatic, means protein is a very complex system. This could add something, the way they have explained through pi-pi stacking. This could add the biochemist to explain this simple concept. And they wrote, thanks for sharing your work. Very glad to see that you used your newly established concept of carbohydrogen bond to explain the mutational effect in our paper. It is very interesting study. So I'm really thankful to them to encourage to do the fundamental science here. So we have a lot of experimental challenges. As I said, these inverted carbon molecules are unstable. So I don't know with the supersonic jet we can form those complexes or not. But we have computed there are proton NMR we can do. That we can do the weight stretching frequency, IR stretchings. We can do the proton NMR. We can do the carbon NMR also to try to give the experimental evidences for this carbohydrogen bonding. So as I said, the last few slides all are the computational. It requires the experimental evidences like the hydrogen bondings with the tellurium and polonium, the hydrogen bondings with metal hydrides, the hydrogen bonding with the inverted carbon without lone pair or pi electrons. These are the experimental challenges that needs to be answered by us or somebody else in this earth. So I'll conclude. So these are the conclusions, the three-line conclusions I have. So less electronegative atoms such as selenium, tellurium. Selenium will prove experimentally it can form hydrogen bonds. Polonium can form hydrogen bonds. Polonium and tellurium, if you go by the Paulink's electronegativity, these are more or less electronegative than hydrogen. and they can form, metal hydrides can form hydrogen bonds, and it deviates from the IPAC definition. Hydrogen bonds can be possible without involving lone pairs of electrons or pi electrons. So there are a lot of challenges, and we have summarized our work, the sulfur selenium part here. There are other than the hydrogen bondings, which controls also the biological activity that is there in this review. If somebody is interested, can go through. As I said, there are challenges are plenty. So I don't know, it is 103 years. There could be another 100 years to answer many of the questions. I cite this one. It's from one of the famous scientists, Feynman. The test of all knowledge is experiment. Experiment is the sole judge of scientific truth. So though we do a lot of theory, but the experiment is experiment. That is the challenge. We have to accept it and do it. So I thank all my teachers, all my students, all my collaborators, and the funding agency. I'm really thankful. During my PhD and postdoc, I got very good two mentors who gave me the freedom to explore whatever I want. I'm really thankful to them to train me and to fall in love actually in hydrogen bonding.
Very nice.
So I thank to all of you for your presence. So there are very simple quote. Anyway, so this talk is dedicated to by the payment literacy to our fathers who has never gone to the colleges. Let me read it carefully. So I dedicate to my parents, though they have never, they don't have very, what do you call the school degrees, but they send their sons to TIFR and IISc to do their PhD. My younger brother did PhD in IISc. I'm really privileged or lucky to do PhD in TIFR. Thank you all of you. I'm really sorry for the interruption.
No, not at all.
Okay.
Of course, which was due to some technical glitches. Thanks very much, and nice picture of NISER, and also ended on a high note quoting Feynman. Also interesting to note that this field, in spite of more than 100 years old, has lots of challenges for younger scientists to explore and find newer methods of studying, insights into this. And also nice to see a lot of your work has been sort of well recognized, and we all wish you and your group a lot more successes to come in the coming years. With that, the talk is open for questions. If there anybody would like to interact or talk or discuss on the Zoom call, please go ahead and unmute yourself and ask the question. And similarly, please type in your questions if you have any. Any questions from Zoom? Okay, so I think by the time, there's one question. Let me see who that is. Yeah, Professor Datar. Yeah, please go ahead.
Can you hear me?
Yeah, we can.
Okay, well, this is, probably not directly related to the hydrogen bonding, but one of the very interesting properties of water, which of course involves two hydrogen atoms, is that it has a large electric dipole moment. So how important are these dipole interactions in the systems that you are studying?
Yeah, it is important. If you look at the water dimer, say mostly the dipole interaction and electrostatic, that one. Mm-hmm. And going down the group, there is also the dipole interactions are there. But at the same time, we have the polarizability. Going down the group, the molecules, the atoms become bigger, and it is more mostly dispersed actually. You will have a lot of polarization effect as well as the dispersive effect.
So another related thing is that this polarizability, of course, must be a tensor, because depending on the orientation of a complicated molecule, let's say containing hydrogen and even other atoms, this would be quite a complicated polarizability function, right? A tensor. Is that correct?
Yes.
So the interactions would be fairly complicated among the,
Very complicated.
yeah.
It's not the way it was thought before. It is completely dipole interaction. That's why they were always telling it should be electrostatic in nature, but that's not that simple.
Yeah. Yes. Okay. Thank you.
Any other questions to Himansu? Yeah, so Himansu, I just want to ask you, so in terms of the instrumentation, of course, one device that you have shown, so is that is completely kind of built operational at NISER or
Yes. Let me go to the sorry. So it is completely built in Niger. Actually, we don't have a workshop like a TI-PAR, so that I always miss.
okay. Yeah, this one.
So yeah, this one we made the drawing, everything, all the design, everything, and it was made in Pune by the Forback, the company.
Okay.
It's operational now. Yes.
Nice. Okay. But so what you meant by saying is that you actually kind of bought or imported certain components, but the entire device is actually
Yeah, yes, like the lasers, the detectors, those are purchased from the companies. The chambers, the mass spectrometer here. So these are from these are actually the custom built. We made the design and the company built it.
Okay.
It's the Forback actually built it.
Yeah, very nice. Yeah, I see that you have
Can I ask a question?
components. Yeah. So who is speaking?
This is Datar.
Please go ahead. Please go ahead.
So this supersonic jet that you use, what is the kind of base pressure in the chamber and what is the local pressure where you make the gas interact with the laser beam?
Okay, so there the local pressure, actually the backing pressure we keep about 1 atmosphere, and that one will be 10 power -6 to -7 torr. So it's about to 10 power -9 pressure differences, torr differences.
I see. So you have, but you don't seem to have roots pumps here. I mean, or
Yeah, we are using the turbo
is the
pumps.
amount of gas very small, therefore you don't require really those big root pumps.
No, but yeah, so it is a pulsing one. It is a 10 also pulsing. So it's not the continuous flow also.
Oh,
so,
okay, pulse. Okay.
Yeah, pulse that.
Typically, what is the pulse rate that you have?
Pulse width.
No, pulse rate.
Rate 10 hertz.
10 hertz. Okay.
Yeah.
Thank you.
Because all our lasers are 10 hertz lasers. So
okay, so you synchronize it with that. Yeah.
Okay. Yeah, yes.
Sanjay has a question or comment.
Hi, Himansu. Very nice talk. Just you go to slide 19.
19. Oh, sir.
You're going the other way. It's 16, 17, 18.
Yes.
19.
Yes. So why this broadband is completely redshifted compared to the sharp ones? I would have expected that to engulf the
that
whole
is
thing.
interesting. That is interesting. So that could
I
be
don't see
paracrystal.
why they should be so redshifted.
That is possible. We have so that could be mostly the paracrystal higher water clusters. Even if it's cyclohexane, we could not remove the waters, and that could be that reason. So if you add a paracrystal 1 water, the blue is 1 water, then 2 water, 3 water, it will be completely redshifted.
How about the solution water phase spectrum? If you just have this aqueous solution.
It is very difficult because the water absorbs there.
True.
In this region.
Okay.
That
because
is,
it's
I can do that
starkly excluding the sharp features. That is what is puzzling.
Yeah.
I mean, is it overwhelmingly higher clusters? And why there is no contribution from the 1:1 complex?
Where? It's a very broad. It should be 1:1. It's there. The blue
1:1 is somewhere near these blue trace, right?
Yes, yes.
And that the thing is your condensed phase spectrum has actually no contribution at the where the blue trace is.
Could be the paracrystal water, sorry, paracrystal dimer also. Higher clusters of paracrystal could be there.
Anyway, yeah. Okay. Thank you.
We have done actually for phenol benzene both solution and gas phase. So we could reproduce the gas phase solution phase spectrum for phenol benzene. It takes 6 to 7 more benzene molecules. Even if they are not directly bonded to phenol, even if the solvation effect has a redshift. It is the solvation effect also, not a secondary effect.
Okay. Okay. Thank you.
Okay. Yeah. Himansu, probably slightly a general question. This was from YouTube audience. So it says, why water is called the universal solvent?
So yes, water is highly polar. The dielectric constant is highly huge dielectric constant. It has a dipole moment. It is a small molecule actually, and it can give hydrogen. It can form hydrogen. Means it can be hydrogen donor and acceptor. So there are many peculiar properties of water is there. So that could be the reason.
Okay.
Universal solvent, it solubilize many of the ionic compounds, but like even if you have a bigger alcohols, or if you have a decanol or something, it cannot solubilize also bigger alcohols. So for small molecules ionic compounds, it would be universal, very universal solvent. For organic compounds, it's not. The organic reactions they do in the organic solvents only.
Thank you. Thank you for that nice answer. So I don't see any more questions from either of the audience. So therefore, once again, I would like to thank you, Himansu, for your very nice talk and also giving a lot of the current directions of the field and also your own groups success stories, and wish you all the best for, as I said, for future endeavors. And with that, I would like to thank you on behalf of TFR Asset Colloquium and also to all the participants. And we wish you and all the participants a very happy new year and a wonderful time to come. Thank you very much.
Thank you very much. Thank you for okay. So should I sign up?